Hello and welcome to this video. In this video, I'll be taking you through tolerance stackup analysis of a simple two-part assembly with assembly shift. So let us take this example. This is an example of two brackets which are assembled with each other using one bolt. This is a cross-sectional view of that. And this bolt or this assembly will have assembly shift, which is shown over here. So the two brackets can move relative to each other based on how the assembly of the bolt is happening. That is called as assembly shift. And if the purpose of the tolerance stackup analysis is to find the maximum width of the assembly possible, that is from A to B, how much can they vary with respect to their maximum, then what is the procedure to calculate that? Let's go through that. So the first step in performing the tolerance stackup analysis is to understand the sources of variation. So for that, we need to look at the drawings of the individual parts. So let us say that the drawing of the two plates or the two brackets is something like this. This is the red color part, this is the blue color part. So there are three major dimensions and associated tolerances with them. That is the thickness, this is 4 plus or minus 0.2. Now these tolerances are arbitrary. They are just for demonstration. They might not be accurate in terms of an actual part which is manufactured with these designs, but just to demonstrate the analysis, the tolerance stackup analysis. So 4 plus or minus 0.2, the location of the hole is defined by this dimension 18 with a tolerance of plus or minus 0.2. This is in coordinate tolerancing. This is not GD&T. So that is also another key point to consider when doing a tolerance stackup analysis. And the size of the hole is 6 with a size tolerance of plus or minus 0.1. Similarly, on the blue color part, the size and the tolerance is the same. The location of the hole is as 16 plus or minus 0.2 and the thickness specifications are the same. And we are having a M5 bolt which is used to connect these two plates. So the M5 bolt, the major diameter of the M5 bolt varies from 4.826 to 4.976. This is just a reference range. Of course, this can vary depending on the manufacturer of the bolts. So the next step, once we have this data, the next step is to create the loop diagram. Now the loop diagram is basically created by forming a chain of the dimensions which are affecting the stack up. So we have to calculate A to B. Now we can start from this line and the first segment will be this dimension, which is this thickness of the red color part. Then the dimension number 2 will be the location of the hole, which is 18. And then there are two assembly shifts. We will understand what is assembly shift. And two assembly shift because there is an assembly shift between the bolt and the red color part and assembly shift between the bolt and the blue color part. So 3A and 3B, two assembly shifts, and then there is the location of the hole in the blue part and then the thickness of the blue part, which is 5. So 1, 2, 3A, 3B, 4 and 5. These 5 dimensions, these 5 specifications contribute to the overall dimension of A to B, which is the maximum width. So this is the loop diagram. Now let us understand assembly shift. Now let us consider the smallest major diameter of the fastener, that is 4.826. We had seen that the major diameter can vary within a range. Consider that the smallest major diameter of the fastener is 4.826 and the largest hole is 6.1 because 6 plus or minus 0.1 is the dimension and tolerance for the holes. Consider that the largest hole and the smallest major diameter of the fastener are being used for the assembly. That is the worst case. So what will be the maximum assembly shift? Now assembly shift is nothing but the shifting of the components. So as you can see, if there is excessive gap over here in between the clearance hole and the bolt, the part will shift towards the left or towards the right. Now when we are talking about maximum width, the blue part has to move towards the right, the red part has to move towards the left. So how much can the blue part move towards the right? What's the worst case condition? That is nothing but the assembly shift. So that is calculated using this formula, that is maximum assembly shift will be 6.1, that is the largest hole, minus the smallest diameter of the fastener, that is 4.826. That is the maximum assembly shift possible will be 1.274. So in the shifted condition in which red is towards the left and blue is towards the right, this dimension will be 1.274 if we are considering the largest hole and the smallest fastener. So the amount the parts can move during assembly due to the clearances in the fasteners is nothing but the assembly shift. This is of course considering the worst case condition, that is when assembly takes place and the parts are assembled as wide apart as possible. It is in the worst case condition. Now with whatever data is available with us, we can create the tolerance stackup table, which is shown over here, which is listing down the sources of variations, the dimensions and the tolerances. So the sources of variations from the loop diagram as shown over here, there are 5 sources of variations. So the first source of variation is the thickness, and it will be positive dimension +4 because it is going from left to right. If it was from right to left, then it will be -4. So if it is going from left to right, it will be +4. And the tolerance associated with that is this one, that is plus or minus 0.2. So that will come over here. Second source of variation is the location of the hole. So the location of the hole can vary from this edge. It can go away or it can come closer by plus or minus 0.2. So the tolerance is plus or minus 0.2 and the dimension is +18. Again, it is plus going from left to right. Then assembly shift. There are 2 assembly shift. Assembly shift between red color part and the fastener, and assembly shift between the fastener and the blue color part. So there can be 2 shifts. So both of these shifts are indicated by plus or minus tolerance of plus or minus 0.637 each. Then the location of the hole. The location of the hole can vary, as with the red part it can vary between plus or minus 0.2 with a dimension of 16. Again, this is plus 16 because going from left to right. We have to be very careful with the direction, plus and minus. The thickness is the last one, which is the thickness of the blue color part, which is again +4 plus or minus 0.2. So then we total out the dimensions. So totaling the dimensions gives us 42. 4 plus 18 plus 16 plus 4 gives us 42. That is the dimension for A to B is 42, and the tolerance associated with it is nothing but the addition of all of the values of the tolerance ranges. So 0.2 plus 0.2 plus 0.637 plus 0.637 plus 0.2 plus 0.2. That will give us plus or minus 2.074. That means that the maximum gap of A to B, or maximum width of the assembly, will be 42 plus 2.074, which is 44.074 mm. This is in the worst case condition, when we are considering that all of the sources of variations are at their extreme. In that case, this will be the maximum width possible of this assembly when we are considering all of the parts to vary to their extremes.